All right, starting into chapter 8, we start dealing with fluids. We get out more of the mechanical aspect. What we've dealt with up till now is a lot of the mechanical aspect of physics, motion, machines, the mechanical part of it. And we start transitioning into a little bit more of the non-mechanical part, the fluids, heat transfers, thermodynamics aspect of physics, which is another branch. If you get into engineering and work through engineering, you have your mechanical branches of things, but then you also have the thermal part of this and the fluids part of this that you deal with a little bit more chemical engineering and the idea of chemical engineering rather than the mechanical aspect, which is more the mechanical engineering. Mechanical engineers do get into thermo and stuff like that, but they more base themselves on mechanical objects and mechanical things rather than the non-mechanical aspect of the ideas. When we have matter, we have three states of matter. Things could either be a solid or a liquid or a gas. Three states of matter. You could be a solid, you could be a liquid, you could be a gas. We're going to deal with more the liquid aspect and the idea of what is called a fluid. And we'll deal with gas also here. When you deal with a fluid, it is a state of matter that has the ability to flow. Didn't I give you the notes? Yeah, I'm messing mine here too. I want to make sure it's all in the right spot. I might have a few out of place. When you talk about a fluid, it's a state of matter that has the ability to flow. And if we take a look at things that have the ability to flow, you have liquid and you also have a gas that has the ability to flow. If you heat your house by natural gas, you have natural gas that is a vapor that goes through a pipe that goes into your house, into your furnace. Your furnace ignites it and causes heat. That's natural gas. That gas has the ability to flow. So when you have a gas that has the ability to flow, and obviously water has the ability to flow also. So you have two of these things. You have liquid and gas that have the ability to flow. If I have a solid, something is a solid. This nut is a solid. In the state that it's in, it doesn't have the ability to flow. If I would pour water on this desk, it would flow. If I would release some air into this, some natural gas, it would flow. When you talk about volume, it's empty space that can be filled. It's the amount of space an object occupies. Volume is empty space that can be filled, or it's the amount of space that an object occupies. That's your volume. You have a volume too. How much space do you take up? What is your volume? Now, when you talk about fluids, fluids is either a liquid or a gas. There's differences between a liquid and a gas. When you talk about liquid, liquid has a definite volume. Gas assumes the volume of the container. This bottle of water has 16 fluid ounces of liquid in here, water. You have 16 fluid ounces of water in here. It's a definite volume. You have no liquid, no water in here. But inside this container, I just fill it up with some bad breath. This container has 24 fluid ounces of air in there. 24 fluid ounces of air. Why? Because that is the volume of this container, 24 ounces. So there's 24 ounces, fluid ounces in this container. Okay, here you have 16 ounces. Now, I could take a look at individual molecules. Liquids are more dense than gases. And we can look at the molecules of this. When you talk about a liquid that is more dense, when you talk about denseness, you're talking about thickness. Okay? When you talk about more dense, it's thicker. Particles of the gas move faster than liquid. The particles of gas move faster than liquid. Liquids are less compressible. You can compress both of these, but there is a certain limit in regards to how much you can compress in a liquid here. Okay, you can only compress so much before it blows out the side. I can continue to compress my gas here, and when I compress the gas, it's a lot easier to be able to compress rather than compressing the liquid. I have to stop somewhere. When I look at this gas, I can press in a lot more. It's more compressible. Okay, you can press it in, you can compact it a little bit more. When you talk about the volume of a liquid, it's the sum of the volume of each individual particle. You have water molecules in here. The volume of a liquid is the sum of the volume of each individual particle. So if I have each one of these individual molecules here, I can add up each individual molecule, and that's the volume of the liquid. When you talk about the volume of a gas, the volume of a gas the volume of a quantity of gas is mostly empty space. Because you have these air molecules that's inside this container here. Are the air molecules butted up against each other? And the answer is no. You have air molecules that there is space in between those air molecules. The water molecules that you have here, one's right on top of the other, and it packs down into a nice, you can measure what is the height of this water here. It packs all together here. So all the water molecules get packed together, where all the air molecules are not all packed together. Okay, the volume of this, I say, is 24 fluid ounces, but does that mean if I added up every air molecule, with each air molecule, when I add them all up, add up to 24 fluid ounces? And the answer is no. When you talk about compressibility, it's the ability of particles to get closer together. We talk about compressibility. Suppose we had movable walls. This wall and this wall are movable, and we can slide them in. And as they slide in, that wall will slide behind this wall. So there's a little sleeve that slides that allows basically both these walls in this corner to keep on coming in. So this wall is coming and this wall is coming. This wall is stationary and this wall is stationary. Well, as these walls are coming closer and closer together, okay, you're still okay where you're at right now. But what's going to happen is as the walls get closer and the walls get moved to here and there, and then the walls get moved to here and there, you guys start getting closer and closer together. You start compressing together, the ability to get closer together. As the wall gets from here to here, okay, now you're just stuck in this corner. The wall is right there and the wall is right there. Now you're just stuck right there. You're being compressed. Okay, you're being compressed. And at some point, you either stop the walls or you get smushed. Okay, you stop the walls, okay, and you're very compact over there and compressed together. Or if the walls keep on going, okay, you're going to get smushed. That's the idea of compressibility. Why is it easier to compress a gas than a liquid? Because a gas is mainly empty space. For a gas, it's mainly empty space. The particles are far apart, just like you're far apart right now. They're not compacted together. And when you start compressing, the particles don't have to get as close to each other. Just like right now, if I would move the wall, if we would move the wall to here and right here, you guys could stay where you're seated. You're not compacted or compressed together. Because all basically we're doing is we're eliminating empty space. Okay, that's empty space back there. This is empty space over here. So we're not really dealing with anything in regards to getting closer together. We're just filling in empty space, empty space. That's the gas particles. You have all these particles that are moving around here. You start compressing, they're going to continue to move around. They're just going to be a little bit closer together. Okay, you're just filling empty space. When you talk about a liquid, though, In liquid, the particles are close to each other already. When you talk about density, it's a measure of quantity per given space. It's a measure of quantity per given space. Talk about mass density. It's the concentration of matter per object. What is the concentration of matter per object? Now the symbol we use for density is like a script P, lowercase p. This is rho, R-H-O, rho. And now we calculate your density. Maybe. There we go. It's mass divided by volume. Whatever the mass is, and we divide it by its volume. That's the object's density. Units, kilogram per meter cubed, is your standard units. And this is a scalar quantity. There's no direction to vectors, or no direction to density. No vector, Victor. What is a mass? A solid more dense than liquid, and a liquid more dense than gas. The masses will be equal, but since solids are more compact than a liquid, and a liquid more than a gas, should be an N in there, than a liquid, and a liquid more than a gas, the volume of the solid is smaller than a liquid, or a liquid smaller than a gas. Except for ice, and we'll talk about ice eventually. Except for water and ice, okay? Whenever you have a solid and you go to a liquid, the volume increases. Or if you go from a liquid to a solid, volume decreases. When we go from a gas to a liquid, volume decreases. Like I said, there's an exception to this, and that is water to ice. When water turns to ice, the volume grows, it expands. And the proof to that would be put a can of pop in the freezer. If you put a can of pop in the freezer, eventually you go back to that can of pop in the freezer, it's completely frozen, but the can is popped and there is a huge mess within the freezer. The reason why is the can of pop soda is a lot of water in there. There's a lot of water in a can of Coke. Okay, so with that a lot of water in a can of Coke, whenever it freezes, it expands. And when it expands, it bursts the container that it's in. So when you talk about ice, liquid to ice, okay, when you go from liquid water to ice, okay, it expands, it gets bigger. That's the only thing it does, get bigger. Whenever you go from liquid to solid and everything else, the volume decreases. If the volume decreases, that means my density increases. If volume decreases, density increases. If I take a look at a liquid and a gas, okay, gas is less dense. Gas is less dense than the liquid is. Okay, so when you talk about less dense, the liquid has basically a smaller amount of volume. Okay, the kilogram of water or kilogram whatever it is going to be the same. The mass is going to be the same, but the volume increases or decreases. If I would take this nut and melt it down into a liquid, the volume of this would increase. And if we would vaporize this, the volume would increase even more. All right, we will stop there today. We'll pick up there on Monday, looking to try to get some sort of evaluation next week, towards the end of the week, over the things that we talked about this week. I don't know if we'll get through the entire chapter, but looking for a quiz sometime next week. All right, the rest of the time is yours.